Good morning, students. I am Priya Sharma of EC Department, SIRT College, Sage, Bhopal, Sage Anandam. Today, my topic is two-cavity klystron on microwave engineering EC 702. So, coming to the introduction portion, what are the contents of this video are introduction of a two-cavity klystron, construction of a two-cavity, its working, performance characteristics, and last is the applications. So, first, what is the two-cavity klystron? This is a klystron having a vacuum tube that can be used either as a generator or as an amplifier or as an oscillator at microwave frequencies. The klystron is a linear beam device, that is, the electron flow is in a straight line which is focused by an axial magnetic field. The velocities of the electrons emitted from the cathode are modulated to produce a density modulated electron beam. So this is the basic construction diagram of a two-cavity klystron containing an electron gun, a buncher cavity, a catcher cavity, and a collector. This is the drift space. So how it is works. And we can give inputs from here and take the outputs from the catcher cavity. So here a very high velocity electron beam is formed by an electron gun which is focused and sent through a glass tube through an input cavity which is known as the buncher and field free drift space and an output cavity known as the catcher to a collector electrode. The anode is kept at a positive potential with respect to the cathode. The electron beam passes through gap A. This is the gap A, students, consisting of two grids of the buncher cavity. These are the two grids of the buncher cavity. And they are separated by a very small distance and two other grids which is known as the catcher cavity with a small gap B. The input and output are taken from the tube via resonant cavities with the aid of coupling loops. Now how it works? Firstly, the RF signal which is to be amplified is used for exciting the input buncher cavity, thereby developing an alternating voltage of signal frequency across the gap A. At point B, on the input RF cycle, the alternating voltage is 0 and going positive. At this instant, the electric field across gap A is 0 and an electron which passes through gap A at this instant is unaffected by the RF signal. Let this electron be called as the reference electron. The electron which comes from here is known as the reference electron. And it travels with an unchanged velocity. At point C, the input RF cycle, an electron will leave gap A later than reference electron ER, called the late electron EL. An electron which comes after early electron is known as the late electron, denoted by EL, and is subjected to the maximum positive RF voltage and hence travels through gap B. This is point A, this is gap B, and this is point C. With an increased velocity, and thus electron tries to overtake the reference electron. Similarly, an early electron that passes through gap A slightly earlier than the reference electron is subjected to a maximum negative field. Hence, this early electron is decelerated and travels with a reduced velocity V0. Therefore, the velocity of electrons varies in accordance with the RF field input voltage, resulting in velocity modulation of the electron beam. As a result, the electrons in the bunching limit gradually bunch together as they travel down the drift space from gap A to gap B. The pulsating stream of electrons pass through the gap B and excite oscillations in the output cavity. The density of electrons passing through gap B varies cyclically with time. That is, the electron beam contains an AC current and is current modulated. The drift space converts the velocity modulation into the current modulation. So basically, when electrons travel from here, first is the reference electron which travels at a normal speed, then the late electron which travels with a high speed, and lastly, the early electron which travels at a smaller speed. They all bunch together over here and is collected by the catcher cavity, and then it is later transferred to the collector. From here we can get the output of the electron bunches. This is how a two-cavity klystron looks when it is used as a component. So I have already told the working of the two-cavity klystron. The first grid next to the cathode controls the number of electrons in the electron beam and focuses the beam. The voltage accelerates the DC electron beam to a high velocity before injecting it into the grid of the buncher cavity. The grids of the cavity enable the electrons to pass through, but they confine the magnetic field within the cavity. Electrons traversing the interaction space when the RF potential on grid 3 is positive with respect to grid 2 are accelerated by the field. The decelerated electrons give up energy to the fields inside the buncher cavity, while those that have accelerated absorb energy from its field. Now coming to the performance characteristics, which is very important for the exam point of view. So here the frequency of two-cavity klystron is between 250 to 100 gigahertz, and 60 gigahertz we use as a nominal. Power handling capacity is 10 kilowatt to 500 kilowatt if used with 30 megawatt pulse stream and the continuous waves. Power gain is 15 to 70 dB and 60 dB is taken as the nominal. Bandwidth is limited to 10 to 60 megahertz and is generally used in fixed frequency applications. Noise figure is 15 to 20 dB and the theoretical efficiency is 58%, which we get 30 to 40%. Coming to the applications, it is used in output power tubes like in UHF TV transmitters, troposphere scatter transmitters, satellite communication ground stations, and radars. And if we use it as a power oscillations between 50 to 50 gigahertz, it is used in a klystron oscillator, which will be our next topic. Thank you so much. Please do share this video, and any outputs, please let me know. Thank you. Sage Anandam.